Hello again. Our next speakers are Marina and Jos, who will talk about designing implants and payloads for embedded devices. Give them a warm welcome.
So, good morning, everybody. Thank you that you came to our talk. Hopefully, you will learn something. Hopefully, you will like it. So, quick few words about ourselves. Sorry. I'm a senior security engineer. I'm specializing on offensive security for critical infrastructures, and my focus is physical damage or how to make something blow up, crash, or go bad by the means of cyber attacks. Yes?
All right, so my name is Jos Wetzels, and I'm a principal consultant and security researcher with Secura, a Dutch security company previously known as Madison Gurkha. And my focus is mainly embedded system security in ICS, automotive, and IoT. And a long time ago, I used to do research on critical infrastructure at Twente University.
So during the talk, you will understand why two of us team up together and how do we basically, how these two different skills which we have there needed to design an OT payload, basically. So this is the agenda. We will be going through all of these points, and we start, of course, from the introduction as always. So this is frequent slide, first of my slides, like here's a plant, what's your plan? So how exactly do you make this blow up? And there are two opinions going on in the industry typically. Well, it's easy because look at there is no security in those industrial protocols. And the second opinion is it's impossible, it's so complex, nobody has that knowledge. So, and typically, the understanding about industrial control system security is about that, how hard it is to hack into the plant and find a magic button. So basically, the complexities are revolving around this, finding this magic button, which you press, and then the plant goes bad. But the point is the button does not exist. You actually have to design it and program it. So this is what we will be talking about. How do we do bad, evil things to the chemical plants? And the point is that all the process, so every payload have to be very process specific, designed to specific plant, and it requires a good process comprehension. And through this talk, you will see what that exactly means, process comprehension. And in general, it's a little bit requires more knowledge and consideration than simply, it's not enough to know what makes a pipe to explode. You need to know what makes the right pipe to explode, and what to make the right pipeline to explode at the right moment so that you will get that boom. So it's not that easy, it's strategic. So setting up the fundamentals for all of us that we speak about the same terms. So industrial control system consists of two parts. You have this supporting communication infrastructure, which is basically governed by the IT security. And you have the physical process, which is already engineering science, and it's frequently called operational technology or OT. And the attacker target is physical process. So the attacker who is able to hack into we are not worried with the attacker who is able to hack into the industrial control system. We're only worried about those who are able to actually engineer damage scenario. So in general, as you already understood, ICS security consists of two parts. One is IT security. Yes, you need to be able to hack into the infrastructure. And secondly, OT security. It's basically causing impact on the operation, process or equipment. And basically, that will constitute attack payload, our topic. And this is where we work together with yours. So in order to understand, so cyber-physical hacking is all about just understanding one concept, control loop, nothing else. If you understand that, you understand cyber-physical hacking. So you have sensors. So process is designed with the set points, and it has to work at a specific pressure, temperature, flow. Sensors measure those states and send the measurements to control system, and it adjusts the actuators like valves, motors, pumps to keep the process close to set point. But controllers cannot do it alone because they have only the local view of the process. That's why you have on top of that, you have also humans, or it's called HMI. And on top of that, because humans are also can have just this small brain, so we have tons of optimization applications which make a complex calculation to optimize our process. So basically, the entire supporting IT infrastructure follows this structure, and this is how it looks like. And you have exactly those layers. You have field instrumentation, sensors and actuators, you have controllers, you have HMIs, on top you have optimization, and of course, management. And the definition of real time goes from bottom to top, meaning that all equipment at the bottom work in the definition of real time, which is around like 10 milliseconds, sometimes 1 second. In robotic, it's nanoseconds. Operators already work on real time, which is equal like 1 to 3 minutes. And optimization application, it's days, weeks, and months. And planning is, of course, like years ahead. So for the attacker, now knowing that, we can understand where do we want to live in this infrastructure to have a meaningful impact. Because if I will be trying to do something from the HMI or from the optimization application, the controllers which sit at the bottom, they will, in between of my operations, which is 1 to 3 minutes, they will try to bring the process back into the normal state. So it's very difficult to win at the top, upper layer. So if you really want to cause very meaningful impact, you have to be somewhere close to the process. So basically, you have to be on the controllers. And depending on which industry you're attacking, those controllers will look slightly differently. But as you can see, those are not PCs. Those are embedded systems. And this is your specialization. So I'm breaking the stuff on the top. He is implementing what I need to do in the embedded systems. So basically, as you understood, we have this concept because it's cyber and physical interplay. We have these attacks are called cyber-physical attacks. And in the mass media, typically, it is believed the attacker wants to make something to explode. The point is, it's not that easy to make something to explode. Why? Because we have safety. Even if the attacker is able to cause some incident and maybe close all the valves and pressure is growing, there are layers of safety protection which will not allow attacker to do so. There will be pressure relief valves which the safety system will open. So basically how it looks like, if you know, like there is a security onion, so there is also a safety onion, which starts from the process design. That is the first layer of safety protection, which is those specific set points. You have then process control or controllers. You have HMI, and on top, if humans already not able to prevent this unsafe state, then the safety instrumented systems are kicking in. So the attacker also have to defeat safety systems so that he will get boom. So you see there is a lot of things to do in that plant. Now, the topic of this talk, which steps the attacker needs to do actually to design the cyber-physical payload. How do you go from looking at the plant with the final binary? So, and the point is that now we will go through the cyber-physical attack lifecycle, which we, and you know, so basically the reason why we do lifecycle, because it's a typical approach to, or method to describe a process of conducting cyber attacks. And if you know how the attackers work, which specific tasks they need to do, then you know how actually find it during the forensic, or maybe even how to stop them. So we've conceptualized these stages of developing cyber-physical attack payload, and note that this is not an execution attack already in the target environment, because the steps will be slightly different. Many of them will go from this diagram, but they will be slightly different, and maybe that will yet another talk. But this is the stages you go to design the payload. So how does this actually relate to everything what we already know? For example, to Lockheed Martin. Well, this is action on objectives. Of course, the previous steps are also relevant because you still need to hack into the infrastructure. But this is actually actions on objectives. Similarly, it's a complete mission in the Mandian attack lifecycle. If you've previously seen the SANS industrial control system cyber kill chain, this is a developed stage. There is also this Mitre attack framework for analyzing attackers. And they just started building it for industrial control systems. And we just don't know yet. We just recently started working with them how to bring our knowledge into this framework. So now we will go through the stages of this of the attack lifecycle. And you would think, like, how designing a payload, like, what access stage is doing in designing payloads? Like, you're designing payload, what are you accessing, how it is relevant? It seems like it is irrelevant, but it's actually not. So access is very important, and you will see why. In the design. So access could be divided into basically three major groups. First, it is the target facility, because you need to get into the target facility if this is your goal. For the discovery, basically reconnaissance, process comprehension, you need to get access to needed assets, like to a specific turbine. And you, of course, need to execute an attack. Extremely popular becoming, and we will look, we will see a few slides later, extremely popular became getting first into the trusted third parties, and from there pivot into basically from the staging target into the intended target. It also allows you through this third party dedicated remote access, you can get to specific assets you need, like a turbine. And also because majority of work in the plants is done by subcontractors, design, programming of the controllers, it's all done by the subcontractors. So you go to the subcontractor to get all the needed information about the target plant. And there are also non-targeted opportunistic targets. We will see them later. Targeting. So how the attacker is selecting actually the target? And the point is, yes, we know several cases of the strategic targeting. It is mostly related to the competition when the attacker would go after specific, for example, petrochemical plant in competition, which is competition with another of a nation state. But mostly targets are selected because it's the most suitable target to achieve a goal. So if you want to basically showcase the capability that, hey, I can shut down electricity in Germany, it doesn't matter which substation to shut down if you just want to set a message. There is collateral victim that it's exactly related to the third targets, third-party victims. So if the attacker get into this like subcontractor, so basically, who is a customer of that subcontractor will be compromised. So you are a collateral victim. And there is opportunistic. Well, that server is just looking into me from the internet. I guess I go there. So, for example, just a few examples. Venezuela, suspected cyber-physical attack. This is a logical target. It is a strategic target because it's 80% of the country electricity is produced in there. And details, and this plant went just an upgrade, and there was tons of information on the internet around that open source, which actually even suggests the internet access to their alarm system. So there was like so much detail about that plant was put online that this is really makes a very attractive target. Similarly, Ukrainian cyber attack in Ukraine on the power substation. There is no strong indication that it was a strategic target because they just wanted to shut down somewhere electricity. It was not about that specific substation. But that was an attractive target because there was a lot of public information. For example, there is a video where you could see all the equipment used in that substation. And for example, you could see that they were using Siemens SimProtect relay, which were actually targeted by the malware. Some companies actually proudly release reports with detailed network infrastructure of that substation. So you basically already have everything you know to go and target that facility. This is the HMI from that facility. Similarly, you probably, if you're in this talk, you've probably heard about Triton clearly. And there is no strong indication that Triton victim was strategic target. It's more likely that actually it was used as a live drill or testing performance. Why? Because and it could be actually pretty much every facility in that region. Because basically if you search on the internet, you will see that Schneider, or basically Invesis, has won pretty much every contract in the petrochemical sector in that region. So every plant is carrying Triconics equipment, so just go select any you want. So, and this is the point that, as you already understood, so depending on what the attacker can find about the facility, it actually can make you a target. It can provoke targeting. And it's really shocking. We already decided we are going to write a blog post about that, but internet is full of proprietary and confidential engineering documentation. Full. We are going to write a blog post to show what stuff you can find in there. So it's just quick examples. You know, for example, this was from one facility. Somebody put on the internet confidential information, several documents about everything about alarm tuning in that facility, which is so important to the attacker. So this is all the alarms, how they configured, how they critical. This is actually a photo from the nuclear power plant with equipment, and actually this is a test of some nuclear rods inside of this reactor. You can find crazy stuff. So, but this is a problem. This is a big problem. It can make you a target, especially a lot of stuff from Indonesia. If I would be an attacker, I would go to Indonesia. So this is what makes you target, how the attacker select targets. But then we have a very big problem is targeting third parties. It became the most prevalent, most preferable method for the attacker to get into the intended targets. So because you can get access to the target facilities, you can get access to needed equipment, we discussed that, and obtaining necessary information. It became such a big problem that, for example, UK and the USA has issued special advisories talking about that the attacker is using this staging targets in order to get into the intended targets. And while as soon as they issued this advisories, actually in Germany, one of the power substation was compromised through the internet service provider, so through the subcontractor, and the ISP was compromised through their subcontractor who get on their switches. So you have two staging targets to get into your intended target. And also, basically, USA now started actually even penalizing companies if their information is somewhere sitting on the internet. So one of the utilities in USA was made to pay 2.7 million because their subcontractor did not put on the open server on the internet their proprietary networking information. So that's the big problem. And this is how the attackers get into their targets. So this is the role of access stage on the design of the damage payload, is because depending on how you got into the facility, where you get, into which part of the facility you get, which information you discovered, they will have the most, that will define what damage scenario you will select to do bad things to that facility. So it's basically, it could be access-driven and information-driven. So now that you understand why we have access in the payload design. So the next stage is discovery, and it consists of two parts. The one is more known and understood for you, basically network reconnaissance. You have to understand what assets do you have on the reconnaissance, and that is, and you will have this, for example, mainly an attack lifecycle. Only that as soon as you will reach that regulatory control level with controllers, then you need to already have to have proprietary tools, because traditional IT tools will not allow you, help you to discover controllers. So you will have to use the proprietary qualities, basically the capabilities of the native protocols to query controller. Hey, who you are, hi, tell me about you, what firmware you have, what is your order number, because we even will be looking for completely different information about those assets. It's not like you're looking for what is your MAC address or something. So, and secondly, what is happening in this discovery stage is you perform process comprehension. So you basically need to enumerate all file shares, all important hosts which can, computers which can host useful engineering documentation about how the plant is built, what it is doing, how it is configured, all the control logic, and so on. And for example, if you see below, we wrote a paper. We took a very simple process with just a vessel and water, and we took stupid Modbus open source protocol, and we took man-in-the-middle attack. Everybody knows how to do man-in-the-middle, but then we needed 12 pages, double column, to describe how much recon on that process and all of the configuration of the controllers and everything we need to do simple man-in-the-middle. So it's not that you just do it. You still need to figure out a lot of things. So the next stage is control, because the previous stage was static. You understand static behavior of the process, but the processes are actually dynamic because they change with the time. And as soon as you change something, you adjust the control, the actuator process is changing. So control is about figuring out the dynamic behavior of the process and the ability of the attacker to maintain controllability of the process and how much he can push it, because the attacker wants to do something abnormal to the process. Is he able to do that? So basically, you will have to probe the process and see the responses of the sensors. And again, this is least understood and studied stage among all. There is no public work. There is this work, which also, that is my work, and there is one talk which is not public by Jason Larson, but that's pretty much it, public knowledge about this stage. And now we will, so basically, I have this use case for you, and I'm really thankful to our guys from the Singapore University who specifically for this talk helped us to conduct experiments so that we could show you something interesting. So we want to kill UF filter in the water treatment facility. You see it in this yellow thingy. And you will see the role of the control stage in this experimentation. So this is the filters, how they look in the water facilities. They're extremely expensive, and if they're not working, you do not have water. So it's a very good target, so if killing a filter. So for example, if you look at the HMI of this specific staging of filtration of water, we will find, we can locate the filter. We see that there is some tubes going into it, but what does it mean exactly? We have no idea. So basically, typically HMI do not contain all the necessary details, so you will have to go and find the piping and instrumentation diagram and see maybe some equipment is missing on that HMI. Well, there is still two pipes, two valves. What do we do with that? And the point is, this documentation, again, will not tell you exactly how to damage the and what you can do with it filter. So for that, you will need actually to go into the PLC code, into the controller code. And then from the controller, we would be able to figure out, and you can see the second pipe is coming from another. So basically from the bottom, I had to explain this, yeah. From the bottom, you have a normal water flow, which will be clean. And from the top, that comes from the another stage, and it is a process called backwash. Backwash is a cleaning the filter from these particles which is collected. And we need to know, so basically the idea is, what if we put two flows through this filter and raise the pressure? Because we know that pressure is very damaging for the membrane of the filter. So now then we, of course, because suddenly the another stage of the process is involved, stage number 6, you need to go somewhere else, hack into another stage, understand everything what's going on in there, get the controller logic, understand it. And from all of that knowledge, from the, especially from the controller's code, we will be able to figure out that there is 3 things which can trigger the backwash process, which we want. It's a preset timer every 30 minutes. If the filter pressure, differential pressure in filter is already above 40 kilopascals, our plant shut down. So, and basically the triggering of these events will be based on the state machine. State machine knows this position of every control actuator in the plant at current moment, and it has to basically, it has to follow this specific state so that you could start both processes. But the most important that the state machine is only in the PLC in the stage number 3, but not in the PLC number 6. And we want to start the backwash process in the PLC number 6. And the process will start in PLC number 6 only by one variable, which goes from the PLC number 3. As you can see, this is a lot of involvement. It's not important to understand all of these details, but it's a lot for the attacker to understand, even to start thinking, how can I execute that attack? Eventually, we were able to execute an attack, and both flows are going through the filter. The pressure is rising. So we now know that the pressure is rising, but how much? That is the point. This is what no code can explain you. You have to do experimentation in the live process. Only then you know if we will be able to raise the pressure which is harmful to the filter. So, for example, on average, and this is experimentation from that plant, from the photos which you've seen previously. So that typically the average pressure is 12 to 13 kilopascals. We are able to reach maximum 98 kilopascals, which is in 8 seconds. Then the process returns in normal in 5 seconds. And note that this information, we now know that maximum what we can achieve is 98 kilopascal. I still don't know, and they don't know. We will need to go to the producer of these filters to figure out whether this pressure is really harmful to the membrane, and for how long we need to maintain that pressure so that it would really break. So that is, but understanding this dynamic behavior is still very important, how much pressure we can ignite. And also this timing parameters like 5, like 8 seconds are very important for us because the operator will see that the pressure is rising. So for example, if in case the breakage is instantaneous and we know how the alarms are configured in the plant, so for example, it is expected that the operator will have that many milliseconds to take a decision, understand the situation, and to react. And if this time is smaller or larger than the time we need to kill the filter, then we don't need to spoof this value because we will be faster than the attacker operator will try to react. So now you understand the importance of the control stage. Well, damage stage is the most interesting because it's the most complex, and Jos will talk more about that in his part, about preventing response and obtaining feedback, because the attacker needs to make sure that no components in the plant are fighting with him while he's trying to break something. And also he needs to have a feedback loop to know, like, am I successful in my attack? And damage can take several forms. It's not necessarily, this is so surprising, it's not necessarily only explosions. You can do, of course, equipment breakage, you can do pollution. This is actually a photo from Germany. Isn't it beautiful? You can make product out of a specification, especially attackers now target additive manufacturing. So you basically mess up with the parts and actually make, it's already happening. You can make increased production costs, for example, more electricity consumption and so on. But the point is also that attack design, so for example, me as an engineer, I can understand the process, I can design an attack. There is still this guy who needs to implement everything for me. And for example, in this stage, so what is, there are many filtration stages in the water facility, utility. And for example, there is also one of the filtration stage which called reverse osmosis. And the water has actually the water very much chlorinated in the water treatment facility, and then it needs to be dechlorinated for this osmosis because chlorine is very harmful for that type of filter. So you have this device called dechlorination, and so what we need to do, so for example, to shut down the dechlorination, we are spoofing the flow value. If it falls below 0.4, dechlorinator think that there is no flow and it stops dechlorinator. So basically all the water goes through unchlorinated. So like, oh, success, success. But guess what? There is this ORP meter in another stage which will be measuring the level of the chlorine before it goes into this reverse osmosis filter. And there the attacker also need to spoof the value into low. But guess what? It is in another stage. It is in another network segment. It's another equipment. It could be some analog controller or something. And if the attacker is not able to spoof that or compromise that part or implement his payload in that part of the process, my design is useless because we cannot implement it. So attack design is not always means success. So in the last stage is called cleanup. And it is also very important stage because in the IT domain, we can steal the data and leave the infrastructure, and you would never even know I was there. In a cyber-physical system, it's simply not an option because you change physical process, it's visible. So basically, the most attractive, so after things go wrong, you want to create the forensic footprint for the investigators so that they would think, what do you want them to think has caused this incident? So something else, but not an attack. For example, you can time the attack to the troubleshooting to bad weather and so on, modify some logs and so on. So now, because as you can see, there is a lot of tasks to do in the plant, which will go into the design and the code of the payload, and therefore, in many cases, so you need to live in multiple parts of the facility, coordinate a lot of attacks. For that, it's not always enough just to have a code of the payload, but you also want to have implant. And Jos will talk more about that.
All right, thanks, Marina. So I'm going to talk a little bit about implementation and OT payload development, which is kind of the implementation part of this talk. So when I'm talking about implants, there are a lot of different definitions possible, but for the purpose of this talk, I'm going to consider it a hardware or a software modification designed to gain unauthorized control over specific system functionality. And when I'm talking about an OT payload, I basically mean a digital implementation of a part of the cyber-physical attack. And these two things can be tightly coupled in one malicious blob of code, or they can be separate components which at some stage work together. So why implant? Sometimes people will wonder, why not just modify the control logic? Because people who are familiar with ICS security, they'll know there is no authentication on most of these protocols, and you can usually just change the control logic, the set points, or send a malicious command. In some cases that might be sufficient, but for more complicated attacks you will require a degree of coordination, feedback measurement, coordination speed, and low-level functionality access that you cannot get by modifying control logic or changing set points, and you will need access to the system itself. Of course, many scenarios will be possible without implants, like the attacks we saw in the Ukraine in 2015 and 16. You don't need any of this stuff for that, but for more complicated stuff, you will need it. So the first thing we need to think about is where are we going to place our implants? So this is like a generalized picture of an ICS infrastructure, and you can implant in various types of equipment, and where you will implant will be designed by the requirements that are handed down to me by Marina, and by the process itself, and by various kinds of specifics and parameters. So you can implant the network equipment, which is basically your switches, your routers, your modems, your serial converters, your gateways, whatever. And it can be used to manipulate OT traffic. It can be used for observing and learning the traffic, so you get some insight into the process itself. Or you can, for example, drop traffic to cause loss of control or loss of view, or suppress an alarm signal. Another part where you will need to implant probably is at the process and safety controllers. So these are basically your PLCs, your DCS controllers, your RTUs, stuff like that. And that might be for different reasons. You might want to manipulate the I/O, you want to measure your attack progress, maybe you want to suppress condition monitoring alerts. For example, if you have a payload that causes equipment to vibrate, you might have a second system that does vibration monitoring and send alerts at a certain point that you want to suppress while the attack is in progress before the actual damage is carried out. And of course, you want to also prevent any kind of automated or mediated safety response. And finally, in some cases, you might have to implant the field devices, which are the sensors and the actuators, in order to spoof sensor data, maybe at a high speed, or override digital safety mechanisms within field devices. Now, how to implant? I'm going to keep this discussion very general and high level because it will differ very much depending on the equipment you're targeting. But in general, when you're implanting controllers and stuff like that, it will look something like this. So the first thing that we want is we want smooth native code execution. So we need access to low-level privileged functionality on these embedded devices. We want to be able to talk to the memory or port map I/O. We want to be able to modify kernel memory objects, logic runtime memory. We want to be able to interact with some kind of persistence mechanism, like being able to write to flash, something like that. And ideally, we do this by means of silent hot patching, by which I mean live modification of running code. Because we don't want any reboots, we don't want any service restarts, and we don't want to cause any process upsets as a result of our implementation activity. So there are many ways to get code execution, many ways to get code execution on many PLCs, but generally they come down to either a firmware download, which we modify, command injection in something like a web interface, a logic download, which is what I'm going to mostly talk about, or some kind of memory corruption, like a buffer overflow or whatever. So a little bit about backgrounds about PLC architectures. So when you have PLCs, they generally come in two flavors. Either they are standalone on the left, which contains like the inputs and the outputs and the core of it, or they are modular. So you have a separate power supply module, you have a CPU module, which is like the brains, and then you have input-output modules, a separate Ethernet module. And all of these modules will communicate over a backplane, which has an inter-module data bus. And that can be like something like VME bus, PCIe, or it can be a little bit more proprietary, like XBus or something like that. And these are generally the internals, like highly simplified of what most PLCs look like. So at the core you have a processor, which can be more high-end, or it can be a small microcontroller coupled to an input interface, which is either directly coupled to the I/O pins or to some backplane data bus. It is able to read from flash, where you store your firmware and your permanent storage. You have your communication interfaces, like your serial, your Ethernet, your wireless for your field buses and your industrial Ethernet. And then you have your RAM, where you store the programs and the data, the input-output variable map, the runtime in applications, and the real-time operating system powering all of that, if there is a real-time operating system. Now, the boot sequence roughly looks something like this. So you have the processor, which starts by boot ROM, which is usually one-time programmable inside this microcontroller. It loads the bootloader into RAM. That will start the RTOS or some custom firmware executive. And there can be various operating systems, which I'll mention later. They'll start basically a couple of tasks. They're a very simple operating system. It'll start the logic runtime as a task, which then interprets or executes the logic program by itself. And this can be done in generally two ways. Either you have the logic program, which is essentially compiled to a bit stream for an FPGA or a CPLD, or you can have it compiled, JIT compiled or interpreted on the microprocessor itself. That looks something like this. So you have your discrete inputs and your analog inputs, which are either directly coming from the pins or the backplane data bus. They come into the I/O interface, then they're stored in the input image table. They're read, the program is executed over these variables, and then the outputs are read to the image table, which is synchronized with the I/O interface and going out to the outputs. So if we have an implant, we want roughly access to this kind of functionality. So if your I/O is port mapped, you want access to the special purpose register instructions in order to be able to interface with this, any kind of I/O instructions that you might need to talk to. If it is memory mapped, you want access to any memory mapped I/O registers, maybe a shared memory buffer, bus interfaces that go to the backplane or communications modules, network controllers. Maybe you want to spoof something on a display, or you want persistence, so you'll need to be able to write to flash. And generally that means that if there is any kind of privilege separation at the level of the RTOS or the firmware execution, you want to be able to live in privileged mode. So that is kind of the takeaway from this kind of slide. Now, implant installation roughly follows these kind of steps, and the ones with a little star are optional in most cases. So if there is any kind of privilege separation, you will need to escalate privileges. Then if there is any kind of diagnostics on the embedded system itself, you will need to disable those in order to guarantee implant stability, because like I mentioned, you don't want this controller to crash, because that might cause the triggering of alarms, that might cause forensics to be initiated, and you want your stealth while your attack is still being carried out. Then you will need to relocate your implant to a suitable place, ensure persistence if you want, because like if you only live in volatile memory, that means that if your controller reboots or it crashes, your payload is gone. So if you want persistence, you will need to modify firmware or the stored logic in flash. Then you need to set your hooks, and then you need to go resident in some way. Now, when you're designing your implant, you have several considerations, and there are essentially two here. You will need to decide between an active or a dormant implant. In the case of an active implant, you have the OT payload tightly coupled to your implant. And the benefit of this is that it limits detection and network forensics exposure, because you have, after the implantation, little communication, again, electronically with the controller. Or you could go for a dormant implant, which is essentially just a backdoor where you deliver the OT payload later. This has the benefit of limiting forensics exposure in a different way, because that means that if you are detected during your attack, you don't actually see the OT payload. Then you'll have to decide between persistence and memory residence. If you want to persist, this might be complicated by code signing, so you need the ability to write to flash, and you need enough space. And you also need, if you do memory residence, you won't survive reboot, but it, like I mentioned, limits forensics exposure. Now, one thing we want of our implants is scalability. We want to do as little work as possible for as many targets as possible. So targeting different vendor systems with similar implant functionality might be complicated because they might be very different. But in the ICS space, the benefit is that there are a limited number of key players out there. So if I'm a state-level attacker, I might construct an arsenal of generic templates for key DCS and safety controllers, and then have a one-time upfront investment with no huge turnover, because these systems don't change a lot over time. One complication is heterogeneity. Anybody who works in embedded systems knows there is a lot of heterogeneity, more than in traditional IT. You have a lot of different processor architectures, a lot of different operating systems, different kind of runtimes, different ways to interact with I/O, which might differ between the same family of controllers. Memory layout might be different, so you will need to do reverse engineering there. And then you might have security features, but let's be real, in most ICS, this is not going to be the big hurdle. Another complication is in-house versus commercial. Luckily for attackers, this is shifting towards commercial. But you might in some cases have, for example, a proprietary system on chip or a proprietary ASIC, which you will need to reverse engineer in order to understand it first. Then you might have a proprietary operating system and a runtime, and you'll need to spend all this time understanding this thing before you can develop your implant. For example, in the TriConnect safety system, which was targeted by Triton, you have an in-house operating system and a runtime, and for the different families, you have different architectures. Like the first one was a national semiconductor chip, and then they moved to PowerPC, but there were different PowerPC architectures, and there were also differences in the operating system. So you need to reverse engineer all this stuff to scale your implant. A counterexample, however, is that with newer equipment and some vendors, especially in the PLC space, you see a rise of commercial RTOSs and runtimes. So what you see a lot is you'll see something like CodeSys running on VxWorks, QNX, or real-time Linux, and increasingly on ARM or PowerPC chips. Now, a keynote here is that you see this more in PLCs, which are a little more open than in DCS controllers, which are a little more proprietary. But on the operating system and chip side of things, things are becoming way more homogenized. Another complication anybody who worked in embedded systems will recognize is resource constraints. So the key takeaway here is that in an embedded system you have very, very little resources available in terms of memory, computing power, all that kind of stuff. So if you're developing your implant and your payload, you better enjoy extreme programming if you want to fit all that stuff in there. And then, of course, there might be security engineering complications. You might have domain and privilege separation, which can be on the main CPU itself between user space and kernel space, or it might be between different chips. Like it might be that you are able to get code execution on one chip, but that the logic is running on a different one, and if there is some kind of barrier, like an I/O MMU or some kind of other thing that prevents you from lateral movement on the embedded system, that is in the way. Things like firmware and logic signing would complicate it, sandboxing, exploit mitigations, and when you're delivering your logic, any kind of key lock might complicate things as well. So a little bit of a case study. We'll delve into some of the internals of the Triton malware here. The Triton malware, like Marina mentioned, targeted a Saudi petrochemical facility, the safety system specifically, in this case the Triconnect safety controllers. And the attack basically went like this. So they got in on the IT side of things, and then because of improper segmentation between process control network and the safety network, they were managed to be able to get execution on an engineering station, which is basically a privileged workstation that allows you to download your safety logic to the Triconnect controller. And what the payload basically did here is they downloaded the logic to the Triconnect controller, and this logic is essentially compiled for the PowerPC chip and executed directly on the CPU without any kind of signing, without any kind of basically sandboxing. So essentially the packet that you're sending says, execute my shellcode, please, which is nice as an attacker. Now, one of the things that people wondered is why didn't they just modify the firmware? Because the firmware downloads were also unauthenticated and unsigned. And it's a little easier to modify that than try to get code execution through the logic. The problem is that when you download the firmware, the controller reboots into download mode, and the actual safety logic that's currently being executed is interrupted, which might cause a process upset. So if you want smooth execution, you will actually need to append to the currently running safety logic, and then the old logic continues running. So that is a very important part to realize when people are developing implants and payloads. Now, installing the implant had one complication here. The safety program itself is executed in user mode. Like, there's no actual separation, but the way it works is you have the MSR register, and it regulates what instructions you can and cannot execute based on a privileged bit that is being set, and that is non-writable for user mode. Now, if you want to relocate your implant and you want to patch the diagnostics and stuff like that, you are modifying basically code memory. So in order for that to apply, you will need to flush the instruction cache, and that requires supervisor privileges. So they needed a privilege escalation exploit. Now, they find an exploit in a system call, the SoStatus system call, that allowed them to modify the MSR register while running in supervisor mode, because it's saved to some global, and then when the system call returns, it restores it. The problem is that they have this supervisor separation for the instructions, but they did not have memory permissions. So even in user mode, you can write anywhere in memory, including to kernel globals. And that gave you basically a write wet where, and that basically allowed you to essentially override these variables to trigger a write wet where situation that allowed them to basically toggle the bit to supervisor mode. And that allowed them to then basically disable the diagnostics RAM check, which is an integrity check between memory on ROM and in RAM, and after that relocate the implant. So in order to ensure residence even with a full logic wipe. So after the implant was installed, they could then basically wipe the logic and still continue running. Then they modified the network command handler. So you had this network dispatch tabler, and then they modified one entry in order to be able to communicate electronically at a later stage with this implant. And finally, allow them to deliver the actual implant, which basically gave them arbitrary read, write, execute access to memory. So there's no actual OT payload, but there is this arbitrary backdoor capability. And why is that important? Because it allowed them to basically bypass the key lock that basically could be turned to run mode at a later stage. So if at a later stage this key was turned, they could still deliver arbitrary OT payloads. So now basically you have God mode over this controller. What are you going to do? You deliver the OT payload at a later stage. Now, in this particular case, the OT payload was not recovered from the incident, but we can speculate about what this kind of stuff looks like, and that's exactly what we're going to do. So OT payloads, right? Take a look at the damage states while I take a sip of water. So essentially, when you are engineering this damage states, I basically get handed down some engineering requirements and engineering stuff from Marina, and then I have to implement this attack, which basically consists of three main prongs. And the first of that is manipulating the process, which can be done directly by manipulating actuators or deceiving a controller or operator about a process state, Then if I'm manipulating the process, I will need to prevent a response. The operators and the safety systems might be fighting back, so I will need to manipulate that as well. And then very importantly, I will also need to be able to obtain feedback, because I will need to know if my attack is being successful or if it's failing, and I will need to synchronize different parts of my attack payloads across these implants that I'm having there. So the first kind of OT payload could be an I/O manipulation payload. And that is a simple concept. I'm manipulating the input-output, but the execution is actually non-trivial. There are many different approaches here, so there might be many different kinds of cyber-physical attacks from the engineering point of view, but the implementations can also vary. And that depends on how the I/O image tables are populated, how the I/O is wired to the execution logic, that kind of stuff. So this is an example for most PLCs, which will be kind of standalone. So essentially, you'll have your memory mapped I/O register directly wired to the input pins and the output pins. And essentially, what I want to do is I want to trap access to that particular address range and then install a hook handler. And I can trap that access in multiple ways. I can set a memory breakpoint. I can patch instructions, which will be necessary for port mapped I/O. I can change memory permissions and then install a custom exception handler or something like that. And then when my hook handler kicks in, I can see if it's a read or a write operation. And then, for example, if it's a read operation, I'll set the pin mode to output, which means that it's not actually being read from, and I can spoof the value in the image table instead of the value that's actually coming in. When it's a write operation, for example, I can set the pin mode to input, so nothing is actually going out, or I can spoof the value that's being written out, and then I can manipulate the I/O. Now, for example, for a controller like Triconex, which is modular, it's a little different because the I/O pins are not directly wired to the CPU. Instead, you have the I/O modules, which come in over a data bus to a dedicated I/O processor, which then makes it available over shared memory. So if I want to implement this same payload on like a modular architecture, I will need to hook access to the I/O portion of shared memory, or maybe I will need to hook the bus handler routines when it's coming in. And that makes it look a little bit different. One complication could be field device limitation. So I might be able to manipulate arbitrary I/O, but it might be the case that I'm saying, okay, close a valve at this particular speed, and then the field device has an intrinsic safety limitation in part of its firmware that says, no, that is inherently unsafe, I'm not going to do that. So we'll need to be able to modify the firmware of that field device as well in order to carry out my payload. And that is something that you'll need to take into account as well. Now, a second kind of payload is alarm suppression, and this is part of preventing this kind of safety response. So again, simple concept, non-trivial execution. What we basically want to do is we want to prevent an outgoing alarm being raised or an incoming alarm from being acted upon. And this might require very different approaches, because an alarm might be raised with a dedicated protocol message, it might be outgoing through some kind of I/O signal, or an alarm bit might be in a flag accompanying a red process variable, something like that. Now, alarms can propagate throughout the process at different stages, be handed throughout different process units even, and then there are two ways. Either we can hide the alarms when they're coming in for the operators or a local HMI, or we can suppress them at the field device level or at the controller level. And we're going to look at this second approach because it's closer to the process. So an example, this is the TriStation software for Triconex, and here we have a simple water tank level alarm. If the water level is either high or low, you raise an alarm. Don't think too much about it. Now, the safety program resides in memory as code, and what we essentially want to do is set the output of alarm always to a fixed false. So what we have to do is we have to find this program in memory, and then essentially find the instruction in this safety logic to patch. And then essentially, this is basically just an OR instruction. And then we just override it with an assigning of a static false. And luckily, PowerPC is a fixed size instruction RISC architecture, so we can override any instruction with any other without worrying about any kind of instruction alignment. And the result of it is like this. On the left, you have the normal result, so the water level is high, and the alarm goes out and says, dude, you have a problem. On the right, you still have a problem, but it says, dude, it's all okay, because it has been patched in memory on the controller. Now, a different approach might be alarm relaxation and tightening. So you might wonder, why do we want to relax or tighten an alarm instead of just suppressing it? Well, it might be the case that we don't want to prevent the alarm from being raised, but we want to change the conditions on it being raised. So maybe the limits when it is being raised, maybe the deadband values, maybe the priority of the alarm that is being raised, for two different reasons, essentially. Either we want to relax them because of stealth reasons during scheduled testing, or we want to tighten them to cause hard-to-resolve alarm storms. Because if we are causing alarms to be raised from this implanted part in a part of the process where the attack is not being carried out, then people are going to do incident response there, which will be very complicated while the actual attack is being carried out somewhere else. This can be basically done by hooking functionality that decides whether to raise an alarm. This can be data, like the limit, priority, and deadband properties of some kind of object in memory, as you see on the bottom. And then essentially we override these values internally in RAM, while if they query the values to the controller, asking like, what is your alarm limit on this alarm, we spoof it and we say it is the original thing that you originally thought was going on. And then they're like, there's nothing wrong here, but we're still seeing alarms that we shouldn't be seeing. Or if you have alarm logic that's implemented in code, then we'll have to modify the code by patching instructions. So those are basically the two approaches to going about this. Then you have implant communication. And that essentially looks like something like this. So the implants that Marina mentioned in the different parts of the process, they will have to synchronize at some point. So essentially, what you have is that you have a process that is in a certain state, and only when it is in that state, I want to, for example, change the air or the medium inflow. And that causes the process to shift to a different state, and only when it is in that state, I want to change the agitator speed, for example. And I need to synchronize the implants that might be in different network segments, and it might all be super complicated. What you'd expect, especially if you come from like a regular IT side, is like, okay, it'll just be some C2 infrastructure and it'll be something that will be spottable over the network. But this is something people don't realize. You might actually not see that much electronic chatter, and not just because of stealth reasons, but because of reasons of synchronization that might be very hard. It might be that you are unable to talk quickly enough. You might have packet loss among these protocols. So in that case, communication will have to go through the process physics. And essentially what that means is that you will need to be able to detect any changes in the process state at a different thing. And that might be, for example, I am detecting a change in the flow rate, which means that a process is going towards a different state. And you can do that, for example, with something that is called a non-parametric cumulative sum algorithm, which you can implement in something that is not that big from a regular standpoint, like 17 kilobytes unoptimized. It's doable if you do that like on a controller level, but if you have to implement this in something like a field device, it might be completely impossible because you might have like two kilobytes of memory or even less. So that essentially brings us to the conclusion, and the conclusion here is that you have these various different stages, and you have different kind of constraints that are essentially being opposed upon us. Like you have the engineering constraints that are imposed on Marina. She imposes them down on us, and then basically essentially it goes back to me, and it might be that you have an attack that is engineered perfectly and theoretically possible, but it might not be possible because of very practical reasons, like, for example, not having enough available memory on a controller, or having basically an analog signal that cannot be overridden through cyber means. So the conclusion is that you have this complicated interplay between engineering and hacking that, that essentially complicates things. And we want to appreciate some people who helped here. And that is essentially it. If there are any questions, I'd like to take them now.
Yes, thank you, both of you, Jos and Maria. And
I wanted to thank also my co-speaker Jos, because I used to work a lot with programmers who were working for me, and like typically like, can you do that for me? And the answer is always no, In programming, the answer is always no, or it will take 2 weeks, blah, 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 And I must admit, whenever I like, Jos, can you do that? He's always, yeah, I can. So I wanted really to praise him for that. So.
Thanks.
so there are no questions. Oh, one question, yeah. Wait a moment.
I was just wondering who hired you to do this research? Was it university?
So I am currently working for Secura, which is a Dutch cybersecurity consultancy company, and we work in different verticals, and one of them is critical infrastructure. And one of the reasons this is important You need to understand the offensive side in order to properly do defense. Because one of the things that you encounter a lot is, especially people coming from IT security, they'll come in and they're like, okay, we compromise this network because it's all super vulnerable, and then we have access to a PLC because there's no authentication, I can change the logic, and then you get a question, now what, right? And then people are like, well, I guess it's bad. But you have to be able to understand how bad. You have to be able to understand why it's bad. You have to be able to understand if that thing that you think is possible is actually possible in order to prioritize your defensive efforts. Because it might be that otherwise you are focusing on the wrong thing. So part of what we do at Secura is try to understand at a very in-depth level what these kind of attacks involve in order to better serve customers during consultancy engagements, during red teaming engagements, during a variety of traditional security services aimed at this very complicated domain.
I've been doing this cyber-physical damage for about 9 years, so in different organizations. And again, I do offensive work because there is almost zero public knowledge how the offensive operation look like. We only know that it's sometimes happening. And so basically, and you know, like we don't even have statistics right now, like what are the most prevalent method for the attackers to do something. So we are creating statistics right now, you know, like we are acting as an attackers. And actually, so I do this offensive work, so my organization always allow me to do so because this is why I'm working for defenses. I'm a security engineer. So basically, I frequently participate in the incident responses, and I'm the only person on the team who actually can analyze forensically the OT part of the attack. So for example, when we look at the HMI, the guy would say, well, I know it was compromised, IT guys. And I was just like, yeah, I will be starting looking at the forensic image of the hard drive, what exactly the attacker have done on the hard drive. Because I can only understand, I know what the attacker would probably be doing on that system. Or for example, in case of Triton, because it's a public information, I was on the incident response team for the Triton attack while being at FireEye. So basically, I've been looking like how the attacker was executing this attack on the controller because there was a lot of activities involved. And I was qualified to understand because I'm working on the offensive security for embedded systems. So yes, so our organizations allow us to do so. But in majority, honestly, it's a hobby. You spend entire weekend preparing slides. You know, like we can be bullshitting in here, but in reality, it's a hobby.
If you're worried about, I don't work for a government or anything like that, which is the most practitioners, I guess, in this area.
But if, for example, after DEF CON, our slides were not immediately available, so those organizations contact us because they want to have our slides immediately because they educate their staff. Because clearly this is very useful
I think it's a valuable area for more practitioners than just people at a government or an ICS consultancy, because it might be that if you see a piece of malware, and in the case of Triton, and you have a particular payload, you might be a good reverse engineer, but you're looking at a payload and you're reverse engineering and you're looking at what is it actually doing, and you don't understand it because you don't understand the context and you don't understand the impact. While if you're seeing a piece of banking malware or you're seeing something like that, you might understand it because you're familiar with this environment, and you need to understand impact before you can understand all the various edges of both defensive and offensive security that are involved. So.
And the frequent comment, which at least I get, I don't know whether yours get, is like, do you think it's ethical to present these topics on the to the larger audience? It's like, of course it is ethical, because if we will not present it, nobody is learning from it. The attackers will learn without our presentation. They probably learn from us as well, but they will learn anyway.
And the people who are most interested in this, they are already doing this kind of stuff
so,
very seriously.
But some people think that it's unethical to do such type of talks. Well, choices.
I would like to underline that you're completely right, because at some point in your life you will have probably a piece of electronics in your body, and then you are the process, and it is fairly important to have a solid understanding of how vulnerable you are at that moment. So
Yeah, it's a valid point also to say that this extends, like not all the details, but it extends across verticals. So part of this also applies like to medical devices, to automotive, to the defense and aerospace sector. So even if you're not, just focusing on industrial control systems, it is very good to have an understanding of what is involved in a cyber physical attack.
Further questions? No. So now it's time for lunch, I think. And thank you again.
All right.